This is day 3 of Unit 8. We started today with this warm-up. So take a couple minutes, pause the video, complete the warm-up, and then play to check your answers. So we started with number 1. So the 15th term is what we're looking for. It's a geometric sequence. We know the 8th term and we know the 12th term. So we would try to use the explicit formula, the geometric explicit formula, which says a sub n equals a sub, let's see here, which says a sub n equals a sub 1 plus, this is geometric, so times r raised to the n minus 1. All right, but the issue is we don't know r and we don't know a sub 1. Now we could put in a sub 8 or a sub 12 in for a sub n, but we still have 2 variables. So remember, we talked about this yesterday in class. You need to, instead of using a sub 1, use the first term that's mentioned in the problem, which is a sub 8. So a sub 8 times r to the we're going to put in 12 for a sub n. So 12 minus, instead of 1, remember we adjusted it, so now it's going to be 8. So that's going to be a sub 12. So a sub 12 is a sub 8 times r to the 12 minus 8 power. So a sub 12 is 354,294. A sub 8 is 4374. And r is to the 4th power because we did 12 minus 8. So then dividing both sides by 4374 and taking the 4th root of that. So we're getting the absolute value of r on the right-hand side, because it's 4th root of r to the 4th, is equal to the 4th root of 354,294 divided by 4374. And when I take that 4th root, I'm getting 3. So r is equal to plus or minus 3. So then I'm going to get the 15th term. So a15 is equal to the first term. Normally I would use first term times r to the n minus 1 power, but we don't know the first term. So once again, we're going to use the 8th term. So that's 4374 times the r value, which we'll use 3 first of all, raised to the 15. And again, it's not going to be minus 1. It's going to be minus where we started, which is 8. So that gives me 4374 times 3 to the 7th. Now, you can also think about the fact that if we put negative 3 in there, we might as well do that at the same time here. So that's going to be negative 3 to the 7th. Well, we're going to get 2 different answers because negative to an odd is negative times a positive is negative. This one's going to be positive. So we're getting positive or negative of 9565938. Again, or the negative. It's 9565938. So those are your 2 possible answers for the 15th term. Okay, number 2, form a geometric sequence with 4 geometric means between 19,683 and 81. Well, I need to start with 19,683, and then there's 4 geometric means, and then 81. So we learned yesterday that if there were an odd number of blanks in between those 2, we would be able to take the geometric mean and find the middle term. However, unfortunately, there's no middle term here because there's an even number of blanks. So we can't use that approach. So instead, we're going to have to figure out placement here. This is a sub 1, 2, 3, 4, 5, and 6. So I'm going to use those numbers and substitute into the explicit geometric formula and solve for r. So when I do that, a sub 6 is equal to a sub 1 times r raised to the 6 minus 1 power. So a sub 6 is 81. A sub 1 is 19,683 times r I don't know raised to the 5th power. So I'm dividing 81 by 19,683. and then I'm taking the fifth root of that, and just r this time because that's an odd root. And when I do that, I'm getting 1/3. So now I just need to take 19,683 times 1/3, and then that number times 1/3, and so forth. And when I do that, I'm getting 6,561 and 2,187 and 729 and 243. Those are the missing values. So 19,683, comma, 6,561, comma, 2,187, comma, 729, comma, 243, comma, and 81. There's our sequence. Okay, so today we started with this example, which is we're going to find the sum of integers from 1 to 100. So first of all, let's make sure we understand what it's asking for. We're going to start with 1. We're going to add the next integer, which is 2, plus the next integer 3, plus we're going to keep adding, and we're going to get to the last term, which is 100. That's the notation we use to show that I've skipped. I didn't want to write all of them out, so I skipped some, and then I picked up and ended with the last term, which is 100. Now, you should recognize that 1, 2, 3, 4, and so forth, that's arithmetic. Now, what we have here, though, rather than arithmetic sequence, because I don't have commas, I have plus signs. So we call that a series. So series are just like sequences, except for they have plus signs in between the terms rather than commas. So series, because they're just like sequences, they can be arithmetic, they can be geometric, they can be neither one. And because they are just like sequences, the formulas that we have already used, the explicit and the recursive formulas, also apply to series in terms of finding specific terms. So they're still going to apply. But now we need to look at some formulas that help us to get the sum. Okay, because I don't think we want to really just add 1 plus 2 plus 3 plus 4 plus 5 plus 6 and all the way to 100. There's got to be a more efficient way to find that sum. So in order to figure out what that formula is, we're going to talk about, I'm going to give you a little story here. I told a story today in class, and the story is about the mathematician who discovered this formula. And his name is Gauss, or was Gauss. Gauss was a brilliant mathematician. And Gauss discovered this formula when he was 9 years old. So pretty amazing that he thought of this when he was 9. So he was sitting in class, and he was a genius. So he really didn't need to pay attention to what the teacher was teaching. He decided he was going to figure out how to answer this question, how to find the sum of integers from 1 to 100. So what he thought about, and this, he was just, kind of thinking of this in his mind. He wasn't actually writing anything down, but what he visualized was putting these numbers on a piece of paper. So I'm just going to kind of demonstrate that. So he pictured putting 1, then 2, then 3, then 4, all the way to the last, several terms, 97, 98. Oops, let me extend this a little bit. 99 and 100. So that's what he was visualizing, putting those numbers on a piece of paper. So remember, we're trying to find the sum of these numbers. So what he thought was, well, I'm going to make it easier on myself. I'm going to fold this paper in half. And so when we fold it in half, 1 is going to touch the last term, which is 100. And 2, it's going to line up with 99. 98 with 3, and so forth. All of those are going to line up when we fold the paper in half. So remember, we're trying to find the sum. So what he thought of is, instead of adding 1 plus 2 plus 3 plus 4, he's going to add the pairs, the numbers that we just paired up. So 101, add those together, 101. 99 and 2, add those together. Again, 101. 98 and 3, add those together. Again, 101. Every single pairing that you combine or add up, get the sum, you'll get 101. So this helped him to realize, well, if I have all those pairings and the pairings add to 101, then I just need to know how many pairings there are, and I can multiply the sum by the number of pairings, and that will give me the sum of the entire series. So that led to discovery of the formula. So for this particular problem, we're going to find the sum of the 100 numbers. So that's the notation we use, S sub 100. And that's going to be equal to, in this case, there's 100 numbers. And we fold that paper in half, so that's divided by 2. And then we're going to take those 50 pairings, right? It's going to be 50 of those, and we're going to multiply by the sum that we got from adding the first term, which is 1, to the last term, which is 100. So for this particular problem, that gives us 50 times 101. And when I take 50 times 101, I get 5,050. So the sum of these 100 terms is 5,050. Okay. Now, that's using the information in this particular example, but let's look at the formula in general. So this is an arithmetic finite sum formula. Finite meaning it has an ending, so we know it starts at 1 and it ends at 100. 100 is the last term. Finite. Infinite would mean it would go on forever, which we'll talk about those another day, infinite series. But finite, it has a beginning and an end. So what Gauss discovered was that S sub n, the sum of however many terms, is the number of terms, 100 we had over here, 100 terms divided by 2, because we're folding that paper in half, and that's going to be multiplied by 1, which is the first term, which is a sub 1, plus 100, which is the last term, which is a sub n. And that is your formula for finding the sum of a finite arithmetic series. Pretty cool that he discovered that when he was 9 years old. Okay, so that's the formula we use for this one. That's the one we're going to use for this next one. So now it says find the sum of the even integers from 2 to 100. So I'm going to do the same thing. I am going to use this formula because it's finite. There's an ending. There's a beginning. It's arithmetic. How do I know that? Because I'm thinking even numbers. So 2 plus 4 plus 6 plus 8 and so forth. Okay, so I know it's even and finite, so I am going to use that formula. So S sub, now I have to think about this a little bit. Hopefully this doesn't cause confusion. So we're starting at 2 and we're doing every other number and we're ending at 100. Well, we just said a minute ago there's 100 numbers from 1 to 100. So if I'm only talking about every other number, from 2 to 100, every other number, then that's going to be half as many. Okay, so there are 50 terms. Now, there is a way that we could calculate how many terms there are, but for this one, it's kind of obvious common sense, so we're not going to do any math to figure that out. But I'll show you that in another problem, how we figure out how many terms there are if it's not quite so obvious. So S sub 50, 50 terms, is going to be equal to 50 divided by 2 times the first term 2 plus the last term 100. So 50 divided by 2 is 25 times 102. And when I do that, I'm getting 2550. So S sub 50 is 2550. Okay, that's how we deal with finite arithmetic series. Next. So we're going to try this one. Again, we have a finite arithmetic series. How do I know? Because I can see 4 plus 9 plus 14. The pattern here is adding 5. So, and I have an endpoint here. Now, 99, be careful with that. 99 means the value of that term, that last term, is 99. It does not mean that there are 99 terms. Okay, there's 99 is the value of the term. So I don't know how many terms there are. This plus dot 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 plus means I skipped some terms in there, and then I'm ending off with the last term, which is 99. So if I know it's finite arithmetic, I'm going to use that same formula again. I'm going to substitute in what I know. So I don't know what n is. Don't know how many terms there are. So I can't substitute that in yet. I do know the first term. And I do know the last term. So substituting in what I could, now I can see what I still need, which is n. And hopefully you realize, well, if this is arithmetic, we know how to find a term number for a sequence. And the sequence is really the same as the series, again, just with commas instead of plus signs. So I can still use that explicit formula, in this case, explicit arithmetic. So that formula is a sub n equals a sub 1 plus d times the quantity n minus 1. So if I fill in what I know the 99 is that term that I'm looking for, the term number for. So 99 is a sub n. A sub 1 is 4. D I can see is 5. And I don't know what n is, so times the quantity n minus 1. So 99 is equal to 4 plus 5n minus 5. So 99 is equal to 5n minus 1. So add 1 to both sides. 100 equals 5n. Divide by 5. And n is equal to 20. So I know that there are 20 terms in this series, and that 99 is the 20th term. So now that I know there are 20 terms, I can substitute 20 in for n. And 99 plus 4 is 103. So 10 times 103 is 1030. So the sum of those 20 terms is 1030. Okay. Next, so we're going to use the fact that we know A1 and D, and we're going to find the sum of the first 50 terms of the series. So once again, we were told it's arithmetic. So I know, again, that I'm going to use the finite arithmetic sum formula. So S sub n equals n divided by 2 times the quantity a sub 1 plus a sub n. I'm going to fill in what I know. So first 50 terms means I'm filling in 50. So 50 divided by 2 times the first term, which is 10, plus the last term. Doesn't look like I know it, but I do know the term number is 50. So I'm going to write a sub 50 rather than a sub n. So now that I've filled in everything I know, it's obvious to me what I need, which is a sub 50. So in order to get that, once again, we'll use the explicit arithmetic formula to get the 50th term. So a sub n is equal to a sub 1 plus d times the quantity n minus 1. So I want a sub 50. So a sub 1 is 10 plus d is 2 times 50 minus 1. So 49 times 2 plus 10 is a sub 50. So that's 98 plus 10, which is 108. So the 50th term is 108. So I'm substituting in 108 for a sub 50. So 25 times 10 plus 108, which is 118 times 25. And when I multiply 25 times 118, I'm getting 2,950, which is my final answer. Okay, let's try this one. Okay, so now we've talked about series. Well, now we need to talk about how we would rewrite series in summation notation, or what we call sigma notation. So this problem, we have this sigma. That symbol there is the sigma, Greek letter sigma. And when you see that symbol in math, it means that you're going to sum or add whatever follows. Oftentimes you'll see that and you'll see a number here like n equals and then a number. That, what I've just indicated there on the bottom, that n equals 1, we call that the lower index. And the number on the top there, number 4, that is the upper index. Okay. So what sigma notation means is that you're going to substitute in the lower index into the equation. So if I do that, I'm doing 2 times, I'm substituting in 1 plus 4. I'm going to add, because I see that sigma means I'm going to add the terms. So then I'm going to go and I'm going to substitute the next highest integer above 1. So that would be 2. So 2 times 2 plus 4. I'm going to add. I'm going to continue substituting integers in until I reach the upper index, and I'll put that upper index in, and then that'll be my last integer that I'll substitute. So I did 1 and 2. Now I'm going to substitute in 3. 2 times 3 plus 4, and I'm going to add one more because the upper index is 4. So 2 times 4 plus 4. Now, it says rewrite the following series as a sum, so I'm going to actually write that out. I'm going to figure out what I get here. So 2 times 1 is 2 plus 4 is 6, plus sign. 2 times 2 is 4 plus 4 is 8, plus 2 times 3 is 6 plus 4 is 10. Hopefully you're seeing the pattern now. 2 times 4 is 8 plus 4 is 12. Okay, so when it says rewrite the following series as a sum, that is my answer. It just means write out the terms with plus signs in between. And that is rewriting the series as a sum. Now, I have to evaluate the above next, which means tell me what that equals. Well, this is a nice, short, easy one. I mean, we always look at easy examples first. But generally, they're not going to be this short, and you're not going to be able to just add them. You're not going to want to add them. So generally, you're going to have to first decide what kind of series it is. So we have looked at that, hopefully, and you've seen that 6, 8, 10, 12, that's an arithmetic series because, again, there's plus signs in between. So I can use my formula, and like I said, generally you're going to want to use your formula because it's not going to be this short and easy. So let's use the formula, even though, yes, this one's obvious, we could just add those numbers. So the formula S sub n is equal to n over 2 times the quantity A1 plus A sub n. Now, when you have decided that it's arithmetic, you really didn't need to do all the terms to decide that. You really just needed to find a couple terms and then look at the pattern. So like if I just did 6, 8, and 10, I can see from those three that it's arithmetic. So now I know to use this formula. Well, to use the formula, I need the first term and the last term. Well, if I didn't already get the first term, I would now get it. And remember, the way that you get the first term is by substituting the lower index into the formula. So again, if I didn't already have that first term, I would do that now, putting 1 in, and I would realize that 6 is the first term. Now, if I didn't have the last term yet, like I said, if you just did a few terms to see the pattern, to see that it's arithmetic, and we didn't get the last term yet, we would now get that because we need it for the finite arithmetic sum formula. So to get the last term, remember, I substitute in the upper index into the equation here, and I would get 12 when I did that. Like I said, we already did that, but if I didn't already have it, that's what I would do. Next, I need to know how many terms there are. Again, this one's quite obvious because we can just look and count and see that there are 4. But oftentimes you will only do a few terms of the series so that you can recognize the pattern. You won't do all of the terms. And so if I haven't figured out what all of the terms are, then I can't just count them. So there has to be an easier way, and that is the following. You take the upper index and subtract the lower index and add 1, and that will give you the number of terms. So let me write that. The number of terms equals the upper index minus the lower index. And after I do that, I add 1. So 4 minus 1 is 3, plus 1 is 4. There are 4 terms. So that's how I know it's S sub 4. Again, not always going to be quite this easy that I can just count. Okay, so 4 divided by 2 is 2 times 18. This sum is 36, which you got that probably quicker by just adding. But again, when it's a nice long series, the formula is going to be much easier to find the sum. So S sub 4 is equal to 36. Now, one other thing you need to point out here, remember, this is what I told you to do to find out how many terms there are, and that'll always work. So upper index minus lower index plus 1, that's the number of terms. Now, if the lower index is 1, like it is here, then you don't even actually have to do that those operations right there. You don't have to do upper minus lower plus 1, because if the lower index is 1, the upper index will be the number of terms. However, I don't want you to get that wrong. The upper index is not always the number of terms. If the lower index started at something besides 1, like if it started at 0 or if it started at 2 or 3, then you can't just look at the upper index and say, oh, it's four terms. Okay, so keep in mind, you can only look at the upper index and say that that's the number of terms if the lower index starts at 1. Okay, if it starts at any number besides 1, then you have to go through this process of upper minus lower plus 1 to figure out the number of terms. Okay, so now we have that figured out, and we're going to move on. We're going to try one more problem. Okay, now we did not get to most of these today in class. I think in most classes I really only was able to cover the first one. So that's the one I'm going to go over here in the video, and then we'll cover the rest tomorrow in class. So now what I'm doing is I'm taking this series and I'm rewriting it in sigma notation. So if I'm rewriting it in sigma notation, I'm going to write a sigma. You can just make what looks like a big E. It doesn't have to be like the fancy Greek sigma. A big E is fine. Now, I always, when I'm writing my own sigma notation, I'm always going to start it at n equals 1 for the lower index. Trust me, it's just easier if you start it at n equals 1. It doesn't necessarily have to be n equals 1, but it's the easiest to start at n equals 1 because, first of all, the upper index is easy. And second of all, the equation that we write is going to be easiest. So it doesn't necessarily have to be a lower index of 1, but I would suggest to always start it at n equals 1 for the lower index. If you do that, then all you have to do is count the number of terms. So there are 1, 2, 3, 4, 5 terms. So because we started at 1, that means the upper index is just 5. Now, the equation that we put beside the sigma, that's easy. It's this explicit formula. Explicit. Now, remember, the explicit formula starts off a sub n equals. Well, this won't involve the a sub n equals part, but it'll be the rest of the formula. So all you really have to do is look at this series and determine if the sequence that represents the series is arithmetic or geometric, and then put the appropriate formula next to the sigma. So when I see 5, negative 10, 20, negative 40, I'm seeing this as a geometric sequence, and the R value is negative 2. And I know that the explicit formula for a geometric sequence is a sub n is equal to a sub 1 times r raised to the n minus 1 power. Now, again, we're not going to include the a sub n equals part, but we are going to include the a sub 1 times r to the n minus 1. And that's what I'm going to put right here beside the sigma. So a sub 1 is 5 times r is negative 2. And I'm going to raise that to the n minus 1 power. And that is my answer. That is putting that series in sigma notation. Okay, so that's all you have to do. Start with n equals 1, draw your sigma, put the upper index as the number of terms. Again, it is the number of terms if we start at n equals 1, which is what I told you to do. And then this is just the explicit formula. Now, remember, you do have to check, is the series arithmetic or geometric, and then put the appropriate formula there. Had this series been arithmetic, I would not be using the geometric explicit formula. I'd be using the arithmetic explicit. But other than that, you're going to do pretty much the same thing on all of these. Okay, and we are going to stop there again because that's where as far as we got in class. We'll do the other 3 tomorrow in class. Okay, so your homework is worksheet 3. Those problems were pages 11, 12. Those problems, do those for tomorrow. Again, stay on top of your work. Important that you are getting the practice in this unit.